Good afternoon. We're going to start session TS26, Progressive Collapse and Structural Analysis. This is a really important subject matter, especially for super tall towers. We have three terrific speakers here. My name is Chuck Beesjack. I'm the Director of Structural Engineering in New York for Skidmore, Ings & Merrill.
My name is Tae-Jin Kim, partner and the division head of Changmin Structural Consultant in Korea.
So we're going to start out. We're going to do the Q&A right after each of the specific talks, so it's clear, it's fresh in everybody's mind. So without further ado, we'll get started.
So I'm going to introduce the first speaker, and his name is Han-Soo Kim, professor of the Department of Architecture in Konkuk University in Korea, and he's going to talk about the evaluation of blast resistance performance of ice columns in tall buildings by computational numerical analysis. Welcome, Dr. Kim.
Thank you, Chairman. Today, I'd like to talk about a very important issue that should be considered when we design tall building as well as mid-rise building. That is progressive collapse. Progressive collapse can be occurred by accident and terrorist attack. One of the causes of this kind of progressive collapse is blast. So today my presentation is one of the efforts to prevent this kind of progressive collapse by blast load. Okay, I will present my study in this order. Okay, let me introduce a little bit about progressive collapse. Progressive collapse is defined by the total collapse caused by local collapse. The characteristic of progressive collapse is failure that is non-proportionate to input. Even though the input is small enough to cause a local effect, but the output of failure is much greater than input. So the example of progressive collapse is Ronan Point apartment that occurred in 1968. And another examples are Murray Federal Building and World Trade Center. Some experts say that World Trade Center is not an example of a progressive collapse because the input of this event is very large. So it's not an example of progressive collapse. Anyway, a lot of research on progressive collapse has been performed since 9/11. There are two kinds of methods to prevent this kind of progressive collapse. The first one is to provide alternative load paths. For this method, the engineer assumed that the column is removed, and then he investigates whether the alternative load paths exist or not. Because determine the failure of a column after blast is very difficult, so he just assumed the column is removed, and then he investigates the alternative load path. This kind of method is illustrated by kind of a guideline, such as GS guideline and DOD guideline. It's used for government buildings. Even though this method is very practical and very easy to use to investigate the possibility of a progress collapse, but it's not appropriate. I think it's not appropriate for a tall building because tall building usually use the very special structural system like this mega column. This is a typical mega column which is used in Taipei 101. It is a very huge the CFT column. So if we assume this column is removed, then we cannot provide an alternative load path with the economic or efficient way of reinforcement. So there is another approach to prevent this kind of progress collapse. There is strengthening the vulnerable column. For example, we provide a very high stiffness and high robust reinforcement for this kind of mega column. So we researched which way exists to prevent, which way is to evaluate the residual capacity by strengthening the vulnerable column. Is that one method using PI interaction diagram. The PI diagram is a kind of graphical threshold by looking at pressure and impulse of the blast. In PI diagram, P means pressure and I means impulse. By looking at the impulse and the pressure, we can determine whether the column is fail or not. But this method has some disadvantage. That is, it just assumed a very simple initial condition. It just assumed 20% of initial stress is given before blast. So we come up with another method to replace this PI diagram. The reason we investigate another method is that the column in a tall building is subjected to bending moment as well as axial force. Like this example, the column is subject to the significant bending moment due to wind load and gravity load. Even though the possibility of concurrence wind load and the blast load is very low, but the corner column, like this picture, is always subjected to significant bending moment. So we have to consider bending moment as well as axial force as an initial stress condition before blast. Okay, this is objective of our study. The main goal of this study is to develop the kind of design chart for ice column, which is subjected to blast load. It should be consider various initial stress conditions due to bending moment and axial force. Also, it should be easy to use. For example, PM diagram, which is a conventional design method when an engineer design ice column. In PM diagram, P means axial force and M means bending moment. It's quite different from PI diagram. Also, the design chart should be based on accurate analysis method. In our study, we used Autodin. Autodin is a very sophisticated nonlinear dynamic program which can calculate structural behavior and fluid dynamics. It's a kind of a hydrocode. So if you use this kind of sophisticated program, then we can predict very accurate structural response due to blast. Okay, we come up with some procedure to develop the design guide. We divided the whole process into 3 stages. There is initial stage, blast stage, and assessment stage. The first one is initial stage. Initial stage is applying initial stress before blast. So we found out that this kind of initial stress is very affect the structural behavior due to a blast load. So we should apply this initial stress condition. As I said, we use the AutoDIN to simulate blast effect, but AutoDIN is basically a nonlinear dynamic program, so it lacks static features. So we have to come up with some way to apply a static load with AutoDIN. So we increase slowly the initial stress without exciting inertia force due to a dynamic effect. So we apply the initial stress during 100 milliseconds. If you see the graph, this is a typical structural behavior of blast. You can see the natural frequency of the column is about 15 milliseconds. So if you apply the static load, initial stress during 100 milliseconds, then it is much close to static load. So we apply the initial stage, initial stress condition during 100 milliseconds. This is a blast load, a very short period, and this is some response after blast. Okay, second stage is a blast stage. This is actual stage when we apply the blast load. The blast load is a very complicated process. The high pressure of the explosive is propagated through the air, so we have to calculate every time step to this kind of propagation. So it takes a lot of time. So for the efficiency of analysis, we cut off our analysis, our calculation. So we set up some criteria. That is, if all of the node is less than 0.1 meter per sec, if this is a velocity, then we assume the actual dynamic response is terminated. So we terminate our analysis. The last part is assessment stage. We have to determine the column is failed or not. So we have to set up some failure criteria. At the preliminary stage, we use the displacement as an index of failure. But the displacement is a little bit vague. The displacement is very rapidly increased in compression failure region, but in tension failure region means the column is a high value of bending moment, low value of compression. When the kind of initial condition is given, the failure mode is a tensile failure mode. Anyway, tensile failure mode, for the tensile failure mode, the displacement is not distinctive we cannot determine the column is failed or not. So we use another index for failure. That is a compression strain. So this is a failure criteria for our study. If the compression strain is more than 0.03, then we consider it's failed. Otherwise, we consider the column has a residual capacity to resist another the axial force or bending moment. The last part is assessment method. We have to find out how much the column can resist the blast load. So we have to find some curve. So this dot represents some initial conditions. For example, this dot means the column is subjected to 20 megapascal for axial stress, 200 kilonewton meter for bending moment. So by doing analysis for each cases, we can determine which case was failed or not. So we analysis every cases to find out failure point. The method we used here is a kind of a bisectional method, which is the mathematical method when you want to find the root of the equation, the kind of a trial error. Also, we use the two stages, two intervals. At first stage, we use the coarse intervals, like these cases. And then once we identify the failed cases, we refine the intervals. So the primary analysis, we use this kind of interval, and the secondary analysis, we use the more defined intervals. By doing this kind of analysis, we can identify the design curve, which indicate the capacity of column against blast load. Okay, this is a typical pressure of a blast. If a blast occur, they generate a high pressure, positive pressure, and then some low negative pressure. So if you want to simulate by a numerical program, we have to simulate this kind of pressure distribution. The Autodin provides a very efficient way to simulate a blast load, like 1D wedge. We tested lots of analysis, and we calibrate the tuning, the output of our study, our analysis. So we compared our result with the experiment and the result from CONEP. CONEP is the empirical equation from a lot of experiment. So we confirmed that our result is good enough to predict the actual blast load. Also, material modeling is required to simulate blast analysis. The material behavior is quite different from normal load, because this is a very high rapid strain rate. The strain change is very high. So the material model for this kind of analysis is quite different from a conventional material model. So the Autodin provides some special material model for concrete and steel. So we use the RH T concrete model and piecewise linear Johnson-Cook model for steel. They required a lot of parameters, so we calibrate each value to match the experimental result. So we carried out some testing analysis to compare the actual experiment. This is experiment of blast load, which is performed by another researcher. We did numerical analysis, and we compared the result of our analysis. And we found out that our result is quite accurate as an experiment. So, this is the actual model of our research. The explosive is placed at 2,000 millimeter from the ground, and the standoff distance is 5,000 millimeter. The size of the column is 100 by 100 millimeter, and the reinforcement detail is shown in this picture. The parameter of our study is the weight of TNT. We changed the weight of TNT as 100 kilometer and 250 and 500 kilogram. For analysis, we use the solid element for concrete and beam element for steel bar. Also, we assumed the bond between concrete and steel is perfect by sharing the node. This is a bounded condition for our study. We want to apply the constant stress, initial stress along the length. So we use the simple boundary condition at both ends. Before investigating the blast load, we carry out some initial analysis. This is the strength capacity of the column calculated by Autodin. It calculated by applying initial stress until failure without any blast load. So you can notice that the capacity is a little bit larger than conventional PM diagram. This is a conventional PM diagram. It's used by practical structural engineer. The wall shape is quite similar to a PM diagram, but it's a little bit larger capacity at compression region, but significant large capacity in tensile region. We assume that this discrepancy came from this kind of difference. In Autodin analysis, we use the tensile strength of concrete, and we use a more accurate material model for concrete and steel. Also, the so-called DIF, dynamic increase factor for a high strain rate, is also considered in Autodin. So these factors apply this little bit increase the capacity of Autodin analysis. So this is the reference capacity for our the column model. So this is on the typical analysis of a column. When you apply the initial stage, initial stress condition, they show the small strain, small damage along the column. But after blast, they show the severe damage at the center and both ends of the column. Okay, this is the summary of our analysis. this left graph shows the capacity of column when he applied 100 kilogram TNT, and the second one is from 250 TNT, and the last one is 500 kilogram TNT. The cross mark represent failed case. The circle mark represent not failed case. For example, 10 megapascal and 200 kilonewton meter, the initial condition is 10 and 200. Then if you apply the 100 kilogram TNT, then it does not failed. It survived. But for this case, for example, a column is subjected to 220 megapascal and 400 kilonewton meter, and then we apply the 100 TNT, then it failed. So the initial condition, which due to bending moment as well as axial force, determine the failure, whether the column would be failed or not. So we have to consider bending moment as well as axial force. Also, we found out that the shape of the capacity is quite similar to PM diagram. So we can come up with some design chart by shifting the conventional PM diagram. As you can see, for the case of 250 TNT, the capacity curve is quite less than this case. The last case, 100 TNT case, the capacity curve is very small. So we connected some threshold point. So this green curve represents the capacity of ice column when he applied the 100 kilogram TNT, and a blue curve represents 250, and the purple curve represents 500 TNT. So, for example, this case, a column which is subjected to 10 megapascal and 200 kilonewton bending moment. If you apply the 100 kilogram TNT is applied, then this column would be okay. But if you apply the 250 kilogram, then this column would be failed. So if we get this kind of curve, then we can predict the column would be failed or not. So it can be used as a design chart for blast load. Okay, let me wrap up my presentation by giving this kind of conclusion. We use the compression strain as a index of failure, so the compression strain is very appropriate for this kind of research. Also, the initial stress condition, which came from bending moment as well as axial force, is significantly affect the structural behavior of ice column after blast. Also, the capacity curve is quite similar to bending, conventional PM diagram. So we can obtain design chart by shifting conventional PM diagram. So that is our finding of this research. Thank you for your attention.
Thank you. Because we want to stay on schedule, we're going to do all the talks and keep your questions because we'd like to have an opportunity at the end of all the speakers to ask questions then. Okay? Thank you, Mr. Kim.
Okay.